Okay, let's look at example problem number 2. So a small human is dragging a heavy rubber-soled shoe by its laces across the sidewalk at a constant speed of 3.35 meters per second. If the shoe has a mass of 1.56 kilograms, what is the horizontal component of the force exerted by the child? Okay, so a couple things that stand out to me. Constant speed, and we know the mass of the object. Now, let's draw a picture of what's happening here. You have a shoe on the ground. It's being dragged by its laces. Okay. Now I want to draw a free body diagram. Force due to gravity, normal force. The shoe's not sinking into the table or rising off the ground, so the acceleration in the y direction is 0, so the sum of the forces in the y are 0. Then we have a force applied. And now my friction, you should be asking yourself, should the friction be greater than, less than, or equal to that force applied? Because it's a constant speed in the x direction, that means that the acceleration is 0, so the sum of the forces are 0. So that would be force of friction, and specifically kinetic friction, right? Now, we have what we're looking for. What is the horizontal component of the force exerted by the child? Okay, so this is what we're looking for. We want to know that horizontal component. So just like before, we're going to look at the sum of the forces in the y direction and then in the x direction. And the reason for this is because we're dealing with friction, which is includes the normal force in that equation. And so it's likely that we're going to have to solve for that and then go here. Okay. So like we said before, it's not sinking into the floor, it's not rising off of the ground. So the acceleration is 0, so the sum of the forces are 0. Now what are those sum of the forces in the y? Well, in the y direction, I have a positive normal force, and I have a negative force due to gravity, or I'm going to add the negative, or minus force due to gravity, and all that equals 0. So force normal is equal to the force due to gravity. And we know that the force due to gravity is the mass of the object multiplied by acceleration due to gravity. Okay? So the mass of the object was 1.56, and acceleration is 9.81, acceleration due to gravity. So 1.56 multiplied by 9.81. So our normal force, 3 sig figs, 15.3 newtons. Okay? Wonderful. Now we know the normal force, so we can plug it in over here when we need to. In the x direction, we're moving at a constant speed, so acceleration is 0, sum of the forces are 0. Now what are those sum of the forces? Well, we have a positive force applied, and then we have a negative force of friction. That's all the forces in the x direction, and that's going to equal 0. Okay? And so really similar to last time, we have, we're going to add the force of friction to the other side. Okay? So force applied is mu k times by the normal force. We know the normal force. Should say force normal. We know that normal force, but what is the coefficient of kinetic friction? Well, this is heavy rubber-soled shoe across sidewalk. So if you look at page 68, we have rubber on dry concrete. We're going to just assume it's dry. Doesn't talk about it raining or anything. The coefficient of static friction is 0.8. The coefficient of kinetic friction is 0.65. So 0.65 multiplied by 15.3 newtons. So this force applied So 0.65 times by 15.3, 9.9 newtons. Okay, we figured out what the horizontal component of the force exerted by the child. Now, if the small human only pulled with half the force above, what will happen? Okay? So if we're only dealing with half this force, so that would be half as much, right? So everything else would look the same. That frictional force stays the same because they're moving with a speed. The normal force stays the same, but the force applied is half as much. Do you see how in the x direction we're no longer balanced? We have a net force that's in the negative direction, so that means we're going to have an acceleration in the negative direction. So acceleration is going to equal some number, some negative number, which means that since we were traveling to the right, and then our acceleration is to the left, that we're going to slow down and eventually stop. Okay, so what will happen? We will slow and eventually stop. If the small human pulls with an extra 2 newtons of force, what will be the acceleration of the shoe? So now we're kind of looking at the opposite situation here. Force due to gravity, force normal. Now our applied force is greater than our force due to friction. Okay. So we now have an acceleration in the positive x direction because the sum of our forces, we have extra force here that's not being canceled in the x direction. This doesn't change though. It's the same object, so the force due to gravity is the same, which means the normal force is the same. So from above, force normal is 15.3 newtons. Now let's look at the x direction. The sum of the forces in the x direction, that's going to equal mass times by acceleration. And this acceleration is no longer 0. Okay? So what are the sum of those forces? Well, that would be the force applied minus the force of friction is going to equal the mass of the object times by the acceleration. Let's plug in numbers to see what we have. If the small human pulls with an extra 2 newtons of force, well, before it was pulling with 9.9, so it would be 11.9 newtons minus the frictional force. And remember, frictional force is mu k normal force. This doesn't change, that doesn't change for this particular situation. So the friction is 9.9 newtons. And that's going to equal the mass, which is 1.56 kilograms. And then we're looking for that acceleration. Okay, so this minus that, 2 newtons, 1.56 kilograms equals acceleration. Divide by the 1.56. So acceleration is equal to 2 newtons divided by 1.56 kilograms. So that'd be acceleration is 1.3 meters per second squared. Okay, where are we at time-wise? All right, so now the last example that I want to look at with you, we have example 3 and 4 and 5, etc. But I think what we should do is look at one question from the assignment that you'll be working on. Okay, and that's what we're going to wrap up this unit with. The other examples are there if you want to get extra practice. A student exerts 36 newtons horizontal force as she pulls a 52 newton sled across the cement sidewalk at a constant speed. What is the coefficient of kinetic friction between the sidewalk and the metal sled runner? Okay, Now, we have a sled being pulled across the ground. Okay, and so we'd have a force due to gravity, we'd have a normal force, and then we're moving at a constant speed. So that means the sum of the forces in the x direction is 0. So that force applied is going to be equal and opposite to the force of friction. Okay. Let's figure out what that normal force is. So sum of the forces in the y is equal to 0. So the sum of the forces would be normal force minus force due to gravity is equal to 0. Or we can add that force due to gravity to the other side. So the force normal is equal to force due to gravity. So force normal, force due to gravity. The question says a student exerts 36 Newton horizontal force as she pulls a 25 Newton sled. Well, now 52 Newton sled. What is the 52 Newtons? Well, that must be the weight. And so don't get weight confused with mass, right? Weight is the force due to gravity. Mass is the amount of material contained. This has units of newtons, so it is our weight, our force due to gravity. Now in the x direction, we're moving at a constant speed, so the sum of the forces will equal 0. We have a positive force applied minus a force due to friction. That's going to equal 0. Okay? So we'll add friction to the other side. Force applied is equal to the normal force multiplied by the coefficient of friction. Remember, that's what we're solving for. We know the applied force, that's the 36 newtons. We know the normal force, that's the 52 newtons, and we'll divide that over to figure out the coefficient of kinetic friction. Okay? Coefficients are unitless. Okay, so that wraps up our example problems for friction. If you're wanting to work on some more of the examples in the notes, and you have questions about those, let me know. Okay.